Welcome back. Let's continue our discussion on acids and bases, and let's talk about neutralization equations, and let's also talk about titrations a little bit. But first, let's talk about neutralization. So we know what an acid is, we know what a base is. What happens when they react together? Understand that when an acid and a base react, they neutralize each other. So the acid will neutralize the properties of the base, and a base will neutralize the properties of an acid. So this happens through the properties that both acids and bases have. And remember that acids are donating protons, whereas bases are accepting protons. Or, if you think about it through the lens of Arrhenius, acids are producing H plus in water, and bases are producing OH in water. So if you think about their two products, what are they going to form? Well, together they form water, right? So let's look at that. A general equation that we can rely on when we're trying to talk about acid-base neutralization is this. We have an acid, some acid, plus some base is going to give us water. I should just write it as water, and a salt, like some kind of salt. Now, this could be anything. It depends on what's the acid and what's the base, right? But the salt is just kind of the leftovers afterwards. So let's look at a couple examples and we'll see how this works. I'm going to do one with you, and then I'm going to let you kind of tackle a couple on your own. So let's look at a reaction between nitric acid and potassium hydroxide. See if you can take a second in this next section here where it says examples. See if you can take a second and write out what nitric acid is and what potassium hydroxide are. So, if you have to pause and do so, make sure that you do so. Hopefully this is what you wrote down. So, nitric acid, remember that it comes from nitrate, and since it's an 8, we're going to change its name to ic, so it's nitric acid, and potassium hydroxide. Now, this is happening in solution, so both of them are aqueous. And let's follow that same pattern that we saw in our example formula, right? So we say that it's going to be HNO3 and KOH is going to form water and salt. But where is the water coming from? Well, if you think about it, the water is coming from H plus and it's coming from the OH minus. So when those things come together, they are going to form that H2O, which is going to be a liquid. And then what are the leftovers? The leftovers are, let's see here, the K plus and the NO3. So we now have this K and the NO3 react together, and that gives us our salt that's in solution. Doesn't mean that it's a solid, it just means that it's the salt, it's just the leftover aqueous salt that is in solution. So that's the general formula. It's going to work out that way pretty much every time. We have an acid, reacts with a base, it gives us water, and it gives us salt. Why don't you try one on your own? Let's try and write the balanced neutralization equation for hydrochloric acid and calcium, let's do calcium hydroxide. So go ahead and give this a try, and come on back when you finish. Make sure you balance, because this isn't a 1-to-1 ratio this time, so double check that. Come on back when you finish. Okay, so the H and the OH combine together to form water, and the Ca and the Cl form together, or combine together to form calcium chloride. So make sure you balance, like I said. It's the easiest thing to do with this when you're balancing. If you remember back when we did our balanced chemical reactions, instead of imagining H2O as H2O, sometimes it's easier to imagine it as HOH, because then you balance the hydroxide group separate. And we know that we have 2 hydroxides on the left, so that means we need 2 hydroxides on the right, which makes balancing this really easy. So think of it that way when you're balancing it. It should make the process a lot easier for you. Let's try a couple more. This time I want you to try out 2 different problems for me. I want you to try out sulfuric acid with lithium hydroxide, and I want you to try out acetic acid with sodium hydroxide. Go ahead and see if you can figure out the products for each of those. Come on back when you finish. All right, hopefully this is what you got. I forgot my states of matter on this bottom one, but don't forget to balance these. That's the important part, of course. Sulfuric acid reacts with hydroxide to form H2O and lithium sulfate. Acetic acid reacts with sodium hydroxide to form water and sodium acetate. So make sure that you're all caught up with that. So let's now transition and talk a little bit about titrations. Titrations are probably the most common chemistry thing that you can do in the lab or otherwise. Titrations are a method of determining moles of concentration of an unknown chemical or solution. We do these constantly in chemistry, and we're going to do one in this class as well. Now, I'm going to read number 2 by just reading the thing outside of the parentheses, and I'm going to read it again with the thing in the parentheses. So, an acid solution whose concentration is known is added to an unknown base, which is either a solid or dissolved in a solution, or a base solution whose concentration is known is added to an unknown acid with either a solid or dissolved solution. So in other words, we have one thing that's known and one thing that's not, and we add the known thing to the unknown thing until they reach what's called an equivalence point. So this is at a point where the stoichiometric amounts of each of them are equal. Not that they have the equal amount in solution. It doesn't mean that if I have 25 liters of a known acid and I add it to 25 liters of a known base. That's not what I mean. I mean stoichiometrically equivalent, meaning based on the number of moles. So once they reach a point where the number of moles are equal, this is what we call an equivalence point. At this point, all of the acid has neutralized all of the base, or all of the base has neutralized all of the acid. So at that point, moles of acid equal moles of base at the equivalence point. It's really important to remember that. Moles of acid equal moles of base at the equivalence. So, a couple of terms to keep in mind here. The thing that we're usually adding, the thing that we know the concentration of, that's what we usually call the standard solution. So say that I have a solution of 0.1 molar HCl and I have an unknown base. The 0.1 molar HCl would be my standard solution. I can determine the equivalence point by using an indicator. Remember, we talked about a couple before at the beginning of this chapter. We talked about litmus. The one that we're going to be using in our own lab is phenolphthalein. So we can use this indicator to determine when a color change occurs. But understand that when it changes color, this is called the end point. Understand that when the color changes, that is not exactly an equivalence point. That is what we call the end point. If you pick a good indicator, the end point should occur at the equivalence point. But understand that they are different things. The end point is when the color changes. The equivalence point is when the moles are equal. But again, a good indicator will be at the same point. So, let's look at the things that we need to do to calculate these sort of things. The calculations involving titrations can seem at first a little bit complex, but honestly, it's kind of stuff that we've seen before. So let's kind of run through it. Let's talk about what happens if we have two solutions of a base or an acid, and we're trying to determine the concentration or the moles of one or the other. So remember, like I said, at equivalence, the moles of the acid equal the moles of the base. So when we define that a little further, if you think back to when we talked about concentration, what that means is that the molarity times the liters of the acid equal the molarity times the liters of the base. So please keep in mind, though, that both of these terms assume that we are at a 1-to-1 ratio. And by that I mean, let's say, for example, I'm reacting hydrochloric acid with sodium hydroxide. That's a 1-to-1 ratio. But if I have sulfuric acid reacting with sodium hydroxide, that is no longer a 1-to-1 ratio. But these assume that I'm talking about a 1-to-1 ratio. So let's rewrite this equation a little bit because I think we can do it a little better. Let's rewrite this as MAVA equals MBVB, meaning the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. Now, this is only applicable if we're talking about solutions, like both of them are in solution, right? Because both of them have a volume. But what if I have a solid? What if I have some solid HCl, and I don't know what the concentration is, or some solid unknown acid, and I have a concentration of known base? Well, then I'm going to do something a little different for that. So I'd encourage you to write this down as well. Let's say that I have a solid acid, then that means I'm only going to use the moles of the acid equal the concentration of the base times the volume of the base. Now let's say that I have a solid base. then I'm going to have the concentration of the acid times the volume of the acid equals the moles of the base. So just keep in mind that if I'm dealing with a solid substance, which sometimes we are, that's the way that I'm going to use those equations instead. Now, we can also use these techniques to determine molar mass of the solid chemicals. We've determined molar mass in the past, so it works kind of the same way, except this time we're just going to be finding moles in a different way. The first thing we're going to do is we're going to determine the mass, which usually means we use a scale or something. Then we're going to titrate it with either an acid or a base in order to bring it to equivalence. And remember, when we're at equivalence, that means the moles of our known thing are equal to the moles of our unknown thing. So then we use that to determine the moles of the unknown from that equivalence point. And now that we have moles, and we also have grams that we gained from the scale, we use that to determine molar mass. So keep in mind again that molar mass is always going to equal to mass over moles. We are determining the mass here in the first step. We are determining the moles in the third step. So that's where we find all the pieces. We put those together. That helps us determine molar mass. So let's do a little practice. Like I said, this sounds like it's kind of complicated, but it's actually a lot easier than you think once you get into it. So let's look at this one here. It says, what is the concentration of an HCl solution if 25 milliliters of it are titrated to the equivalence point by 45 milliliters of a 0.2 molar NaOH? So let's kind of break down what we have, right? We know that this is our acid. We know that this is our base. And this is our standardized base, meaning that we know the concentration of this solution. We don't know the concentration of the other one. So they're both solutions. So that means I'm going to use my MAVA equals MBVB. Now be careful. You might think, oh, this is exactly like dilution. So I'm going to take those volumes, I'm going to add them together. No. This is different. We're talking about the base by itself and the acid by itself. So it's really easier than dilutions. It's just plug and chug. So think about what you need to calculate, how you should manipulate that equation, plug in the values that you need, and see if you can solve it on your own. Go ahead and pause and come on back when you're done. Hopefully you realize that what we're looking for is the concentration of our acid. So we manipulate the equation to solve for concentration of acid, and I just plug stuff in. Plug in the 0.2, plug in the milliliters. Notice that I did not convert into liters. You're welcome to if you'd like, but the milliliters cancel here, so there's really no reason. So you just kind of plug in what you have, and you get a concentration. Notice that I labeled what this was. I said it was 0.36 molar HCl, because that's helpful for me to know that now I understand, based on my titration, I know the concentration of the NaOH, and now I know the concentration of the HCl. So those are two very valuable pieces of information for me. Let's take that information, let's use it for the next problem. So it says, suppose 20 milliliters of the previous acid is used to titrate 1 gram of an unknown base to its equivalence point. Calculate the molecular weight of this base. So now let's think about what we need, right? Last time we had 2 solutions, but do we have 2 solutions this time? I don't think so. So we might need to use a different equation. See if you can take this one from the top. Use the information from the previous problem, meaning the concentration that you calculated previously, and see if you can figure out the molecular weight of this base. I'll let you try it out, and if you get stuck, well, you can unpause and check it out. But otherwise, I encourage you to give it a try. Come on back when you're finished. All right, let's walk through it. Hopefully you realize that you had a solution of acid and a solid of base. So first thing I'm going to do is I'm going to solve for moles. When I solve for moles, Ma times Va gives me moles of acid, technically, right? Because that's moles of hydrochloric acid times liters of hydrochloric acid, and that gives me moles of hydrochloric acid. But remember that at equivalence, the moles of acid equal the moles of base. So that means that the moles I calculated work for both. I take those moles, I plug it into molar mass. I tried to color code so you see where the numbers are coming from. I have grams on top, moles on the bottom. Bada boom, bada bing. I get 139 grams per mole. Technically, this is the more correct answer because it asked me for molecular weight. And that's it. Those are titration calculations. We will, of course, practice this a little more because we're going to do a lab about this very thing. And if you have any questions, make sure you let me know. We'll see you next time. Bye-bye.